Breathe in and out. Feel the space you occupy, the gentle weight of the air on your skin, the quiet thrum of your own existence. Now imagine for a moment that you could hold in your hand a single grain of sand. Feel its texture, its tiny, insignificant weight. In our Milky Way galaxy, our cosmic home, there are more stars than there are grains of sand on all the beaches of our entire world. Let that thought settle, not as a startling fact, but as a gentle truth. Each one, a distant sun, a potential campfire in the vast, cosmic night. And around so many of them, we now know there are planets, worlds of rock and gas, of ice and fire, countless islands in an endless, dark ocean. We float on one such island, a fragile blue marble suspended in the velvet black. We have built cities, written symphonies, and fallen in love. We have looked up at those myriad points of light for all of our history and whispered the same timeless question. A question that echoes in the deepest chambers of our hearts. A question that connects the first human who ever stared into the night sky with the astronomers now peering through the most powerful telescopes. It's a question of profound simplicity and infinite complexity. Are we alone? This question isn't born of fear. It is born of wonder. It is the ultimate expression of our desire to connect, to understand our place in the grand, silent tapestry of existence. Tonight, we are not going to shout into the void. We are going to listen. Before we begin this quiet journey together, if you find solace in these explorations of the deep and the beautiful, consider subscribing to our channel. By liking this video and sharing it with another curious soul, you help us continue to create these spaces for calm reflection. Your support is a gentle echo that lets us know we are not speaking into the void. Now, let us begin. A journey into the quiet. Come, settle in. Let the noise of your day fall away like dust motes in a sunbeam. We are about to embark on a journey, not one of speed or of noise, but of quiet contemplation. We are going to drift together through the vast, silent halls of the cosmos, and gently hold in our minds one of the most profound ideas humanity has ever conceived: the possibility of life beyond our world. This is not a quest for monsters or invaders, for drama or for conflict. It is a search for a reflection, a search for a kindred spark in the immense, overarching darkness. The question, are we alone? Is not an accusation against the universe for its silence. It is a poem. It is a song we sing to the stars, hoping to one day hear a harmony in reply. For millennia, this question was the sole domain of philosophers and dreamers. It was a thought to be pondered under the moon, a story to be told around a fire. But in the span of a single human lifetime, something remarkable has happened. The question has moved from the realm of pure imagination into the quiet, patient laboratories of science. We have begun to learn the language of the cosmos, and we are using it to listen. In our time together, we will explore this gentle search. We will begin by understanding the recipe for life itself, the humble, common ingredients that the universe provides in astonishing abundance. We will learn that the building blocks of you and I are not precious or rare, but are scattered like dust on the cosmic winds. Then we will become cosmic cartographers, mapping the places where life might take root. We will journey to the rusted plains of Mars and dive into the hidden, dark oceans of icy moons within our own solar system. And from there, we will gaze further, to the thousands of new worlds we have discovered circling distant suns, the exoplanets. We will learn what makes a world just right for life as we know it, a gentle haven in a violent universe. Afterward, we will tune our senses. We will discover the ingenious ways we can eavesdrop on the chemistry of a world light years away, searching for the faintest whisper of life's breath in its atmosphere. And we will learn of the great, silent effort to listen for a deliberate signal, a call from another thinking mind. And finally, we will sit with the silence, the profound and sometimes unsettling quiet that has met our search so far. We will contemplate the Fermi paradox, the great cosmic mystery of why, in a universe that seems ripe for life, we have so far found none. We will not treat this silence as an answer, but as a deeper question, a meditation on our own uniqueness, our own potential, and our own responsibility. This is not a video of facts and figures to be memorized. It is an invitation to feel a sense of connection to the grand scale of reality, to feel the awe of the unknown, not as a void, but as a space of infinite potential. So, let your mind be still. Let your curiosity be your guide. We are travelers on a sea of stars, and the journey itself is the destination. The whispers of chemistry, life's humble ingredients. Before we can search for something, we must first understand what it is we are looking for. What is life? It is a question that has puzzled our greatest minds. We see it all around us, in the unfurling of a fern, the beating of a heart, the silent wisdom in an old tree. But to define it, to pin it down, is like trying to capture the wind in a jar. So, for our journey, let us not try to capture it. Let us instead look for its ingredients, the recipe. If we were to bake a cake, we would need flour, water, sugar, and heat. The universe, in its own patient cosmic kitchen, uses a similar, surprisingly simple recipe for life as we know it. The primary ingredient, the flour of life, is an element called carbon. Carbon is a social atom. It loves to connect. With 4 available arms or bonds, it can hold hands with 4 other atoms at once, or form double and triple bonds, creating an astonishing variety of structures. It can build long, elegant chains like the spine of our DNA. It can form sturdy, intricate rings, the basis of sugars and proteins. It is the ultimate cosmic Lego block. It is stable enough to build reliable structures, yet flexible enough to create the near-infinite complexity that life requires. And the universe is generous with this element. Carbon is not forged in the heart of a special, life-giving planet. It is forged in the heart of dying stars. When a star like our sun grows old, it swells and begins to fuse heavier elements. In its final, magnificent breaths, it cooks up vast quantities of carbon and then, in a gentle cosmic sigh, it puffs its outer layers into space. These stellar winds seed the clouds between the stars with the very stuff of life. The atoms that make up your body, the carbon in your cells, were once inside a star that lived and died billions of years ago. You are, quite literally, made of stardust. This is not poetry. It is physics. And it means that the fundamental building block for life is everywhere. The cosmic flour has been scattered throughout the entire kitchen. But flour alone is dry. It needs a medium, a liquid to allow the ingredients to meet, to mingle, to dance. For life on Earth, that medium is water. Water is a magical molecule. It is simple, 2 tiny hydrogen atoms clinging to 1 larger oxygen atom. But this arrangement gives it a special property. It is polar. One side is slightly positive, the other slightly negative. This makes it a universal solvent, the cosmic womb. It can gently cradle other molecules, pull them apart, and allow them to interact in new ways. The complex chemical ballet that leads to life happens in water. It shields its contents from harsh radiation. It remains liquid across a wide, stable range of temperatures. It is the perfect stage for the drama of biology to unfold. And like carbon, water is not rare. Hydrogen is the most abundant element in the entire universe, created in the Big Bang itself. Oxygen is the 3rd most common. Together, they form H2O, a molecule so common that we see its signature in vast, interstellar clouds, on the surface of distant planets, and frozen in the comets that wander the darkness like icy ghosts. The cosmic water is flowing everywhere. Finally, our recipe needs a spark, an energy source. Flour and water sitting in a bowl will not become a cake on their own. They need heat. Life, too, needs energy to power its intricate machinery. The most obvious source is a star. A gentle, steady star like our sun provides a constant stream of light and warmth, which plants on Earth have learned to harvest through photosynthesis, turning light into life. This is the energy that powers almost our entire ecosystem. But is that the only way? We have learned, in the deepest, darkest parts of our own oceans, that life is more tenacious than we ever imagined. Miles below the surface, where no sunlight has ever reached, we have found entire ecosystems thriving around hydrothermal vents. These are cracks in the ocean floor where the planet's internal heat spews out a rich soup of chemicals. Here, life does not eat light. It eats chemistry. It thrives on the heat of the world itself. This discovery was a revelation. It untethered our idea of life from the surface of a planet. It meant that life could exist in the dark, hidden places, in the subsurface ocean of a moon far from its star's warmth, kept liquid by the gravitational pull of its parent planet. It dramatically expanded the number of potential homes for life. So, let us pause and reflect on this. The three key ingredients for life as we know it: a versatile building block like carbon, a liquid solvent like water, and a source of energy, are not rare, precious commodities. They are among the most common, most abundant things the universe makes. The cosmos is not barren. It is a fertile ground, seeded with potential. It is a vast garden, waiting. The question, then, is not whether the ingredients exist. The question is whether, on some other world, in some other corner of this garden, they have ever been brought together by time, by chance, by the gentle, patient laws of chemistry, to begin their own quiet song. Habitable worlds. Searching for cosmic shores. With a recipe in hand, our search for life becomes a search for kitchens. A search for the right kind of place where these ingredients can be gently mixed for billions of years. A place we call a habitable world. For a long time we only knew of one, our own. But our perspective is changing, faster than ever before. We are beginning to draw the maps of new potential shores. Our first instinct is to look for worlds like our own. Planets orbiting a star at just the right distance. Not so close that the water boils away, and not so far that it freezes into a permanent, lifeless ice. This temperate region, this gentle coastal zone of a star system, is poetically known as the Goldilocks zone. The idea is simple, but its implications are profound. Every star, depending on its size and heat, has a Goldilocks zone. Hot, bright stars have zones that are wide and far away. Cool, dim stars have zones that are narrow and close in. Our journey now is to find planets, specifically small, rocky planets like Earth, orbiting within these promising regions. Let us begin our search close to home, within our own family of planets. Here, the story of habitability is a tale of what was and what could be. Consider Mars, our neighbor. Today it is a cold, dry desert world. Its atmosphere is a whisper-thin shadow of its former self. But the evidence written on its surface tells a different story. We see ancient riverbeds carved into the rock. We see vast deltas where water once flowed into enormous crater lakes. We see minerals that, on Earth, only form in the presence of liquid water. Mars was once a warmer, wetter world. It had the ingredients. It was, for a time, a habitable shore. A profound question haunts us as our robotic rovers crawl across its surface. Did life begin there? In that ancient Martian ocean, did the chemical song begin to play? And if it did, could its fossilized remains, or perhaps even simple, hardy microbes, still be hiding in the soil or in underground water deposits, waiting to be found? The search on Mars is not just for alien life. It is for a lost branch of our own potential family tree. Now, let us travel further from the sun, far outside the traditional Goldilocks zone, to a place where we thought life was impossible. Let us visit the moons of Jupiter and Saturn. Here we find a new kind of habitable zone, one powered not by the light of a star, but by the sheer force of gravity. This is Europa, a moon of Jupiter. Its surface is a shell of ice, kilometers thick, cracked and grooved like an old skating rink. But beneath this ice, we have powerful evidence for something extraordinary. A global, liquid water ocean. An ocean that may contain more water than all of the oceans of Earth combined. How can it be liquid so far from the sun? The answer is gravity. As Europa orbits Jupiter, the immense gravitational pull of the giant planet needs and squeezes the moon's interior, creating friction and heat. This tidal heating is enough to maintain a vast, hidden ocean. Imagine it, a dark, silent world of water. And at the bottom of this ocean, on its rocky floor, there could be hydrothermal vents, just like the ones on Earth, gushing heat and chemical nutrients into the water. The perfect cradle for life to begin, completely independent of sunlight. A hidden second genesis in our own solar system, We dream of one day sending a probe to drill through that ice, to release a submarine into that alien sea, and to turn on its lights in a place that has been dark for 4 billion years. What might we see, swimming in that lonely light? And Europa is not alone. Saturn's tiny moon, Enceladus, also has a subsurface ocean, and it actively sprays geysers of its ocean water out into space through cracks in its southern pole. We have flown a spacecraft through these plumes and tasted them. We found water, salts, and complex organic molecules. All the ingredients in a warm, wet environment. The invitation could not be clearer. These discoveries within our cosmic backyard have utterly transformed our thinking. They tell us that habitable doesn't just mean a sun-drenched, Earth-like surface. It can mean a dark, hidden place, a world within a world. It has taught us to be more creative, more open-minded in our search. But the true revolution has come from looking further afield, to the stars. For centuries, planets around other stars, exoplanets, were pure speculation. We couldn't see them. They are too small, too dim, and too close to the blinding glare of their parent stars. But we have developed ingenious, indirect methods to find them. One method is called transit photometry. We stare patiently at a single star. We watch its light. If a planet's orbit happens to be aligned just right, it will pass in front of its star from our perspective, causing a tiny, temporary dip in the star's brightness. A mini eclipse. It's like noticing a moth flying in front of a distant streetlight. The dip is minuscule, but our instruments are now sensitive enough to detect it. By watching these dips, we can learn the planet's size and how long it takes to orbit. Another method is to watch the star for a wobble. A planet doesn't just orbit a star. They orbit a common center of mass. A large planet, like Jupiter, will cause its star to make a small, but detectable circular or elliptical motion. It's like watching a person walking a very large, energetic dog. The person gets pulled around a bit. We can detect the stellar wobble by watching how its light gets stretched and compressed as it moves towards and away from us. The Doppler effect. Using these methods and others, a quiet revolution has occurred. We have gone from knowing of only one solar system to knowing of thousands of them. We have confirmed the existence of over 5,000 exoplanets, and that number grows every week. We have found hot Jupiters, orbiting their stars in mere days. We have found super-Earths, rocky worlds larger than our own. We have found planets orbiting 2 stars at once. We have found entire systems, packed with planets, utterly different from our own. The data suggests that planets are not the exception. They are the rule. On average, there is at least one planet for every star in the sky. Think back to that grain of sand. A star. And around it, likely at least one world. A potential island. In our galaxy alone, there could be hundreds of billions, perhaps trillions of planets. And some of them are the right size and in the right place. We have found dozens of potentially habitable Earth-sized planets in their stars' Goldilocks zones. Worlds like TRAPPIST-1e, Kepler-186f, Proxima Centauri b. These are not just designations. They are destinations for our imagination. They are real places, new shores waiting to be explored. We cannot yet see them. They are, for now, just points of data. But they represent a fundamental shift in our understanding. We are not an island in an empty sea. We are an island in a vast, crowded archipelago. The cosmos is teeming with worlds. The kitchens are ready. The ovens are warm. The question that hums in the quiet spaces between the data is, on which of these countless worlds has the recipe been followed? Main Content Section 3. The Cosmic Ear, How We Listen for a Reply. We have found the worlds, countless potential homes. But how can we bridge the immense, silent gap of light years that separates us? How can we possibly know what is happening on the surface of a world we can never visit? We cannot send a probe. We cannot see the surface. We must learn to read the light. We must become interpreters of the faint, ancient messages that have traveled for decades, or centuries, or millennia to reach us. We must learn to listen with our eyes. This delicate art is the search for biosignatures. A biosignature is a sign of life. It is a clue, written in the language of chemistry, that something biological is happening on that distant world. Think of it like this: the atmosphere of a planet is its breath. And by studying that breath, we might be able to tell if there is life there. The primary tool for this is called spectroscopy. Every element and every molecule, when light passes through it, absorbs very specific colors or frequencies of that light. They leave a unique fingerprint, a barcode. When starlight passes through the thin sliver of a planet's atmosphere on its way to our telescopes, the gases in that atmosphere leave their barcode imprinted on the light. Our telescopes, like the James Webb Space Telescope, are designed to capture this faint, filtered starlight and spread it out into its rainbow spectrum. We can then read the barcode. We can see the dark lines that tell us there is water vapor. We can see the signature of carbon dioxide, or methane. And this is where the search becomes a subtle detective story. What would be the smoking gun for life? One combination we look for is oxygen and methane. On Earth, oxygen is overwhelmingly produced by life, by plants and cyanobacteria through photosynthesis. Methane is also produced by life, by microbes in swamps and in the guts of animals. These two gases, on their own, don't like to exist together. They react and destroy one another. To find them both in large quantities in the same atmosphere would be a puzzle. It would suggest that something is constantly, actively replenishing them both. And the most elegant explanation for that something would be a planet-wide active biosphere. Life. It would not be definitive proof. We must be patient and humble. There may be strange, non-biological geological processes on other worlds that we don't yet understand. But to find a distant atmosphere rich with the breath of life would be a watershed moment in human history. It would be the first time we truly knew that our song is not a solo. This search for biosignatures is the search for any life, simple or complex. But there is another, older search. A search for something more specific. A search for a mind, for technology, for a deliberate signal sent by another intelligent civilization. This is the search for extraterrestrial intelligence, or SETI. If the search for biosignatures is like listening for the sound of a distant jungle, the roar of wind and the rustle of leaves, then SETI is listening for the sound of a drumbeat. A clear, unmistakable, artificial signal that stands out from the cosmic noise. The universe is radio loud. Stars, pulsars, and galaxies all produce natural radio waves. It's a cacophony of static. Cosmic ocean roaring. The hope of SETI is that an intelligent species, wishing to make contact, would choose to broadcast a signal that is obviously artificial. A narrowband signal, like one of our own radio stations, which is very different from the broad, messy static of nature. Or a repeating mathematical pattern. A prime number sequence. A message in a bottle thrown into the cosmic sea. So far, the search has been met with a profound silence. But the scale of the challenge is immense. Where do you point the telescope? At which of the billions of stars? And at what frequency do you listen? The radio dial is vast. There is a concept, however, that gives searchers hope. It's called the watering hole. It's a quiet slice of the radio spectrum between the natural emission frequencies of hydrogen and the hydroxyl molecule. Hydrogen and hydroxyl, H and OH, together make water. The idea is that any water-based life form, like us, might see the poetry in this. They might choose this quiet, meaningful channel as the logical place to broadcast. A universal meeting point for civilizations to gather and drink from the well of knowledge. It is a beautiful, hopeful idea. And we have not only been listening, we have, on a few rare occasions, sent our own quiet messages out. In 1974, from the Arecibo radio telescope, we broadcast a simple pictorial message towards a star cluster called M13, some 25,000 light-years away. It was a simple postcard. It said, "This is who we are. This is what we are made of. This is where we live. Hello." The message is still traveling. It has not even completed 0.1% of its journey. It is a monumentally patient and hopeful act. A whisper sent into the vastness, not expecting a reply in our lifetimes, or in the lifetimes of 100 generations to come. But it is an expression of our own deep desire to be known. And so we listen. We listen for the chemical breath of a biosphere in the light of a distant star. We listen for the deliberate, intelligent pulse in the static of the cosmic radio. We are straining our ears, using the most advanced technology we have ever built, to hear a reply to a question we have only just learned how to ask. And what we have heard, so far, is the subject of our deepest meditation. The silence. Main content section 4. The eerie quiet, contemplating the Fermi paradox. Let us sit, for a moment, with this silence. We have journeyed through the cosmos and found it to be fertile. The ingredients for life are common. The number of potential homes of planets in habitable zones is staggering. Billions, perhaps trillions, in our galaxy alone. And our galaxy is but one of hundreds of billions. The universe has had over 13 billion years to work. Ample time for life to arise, for intelligence to evolve, and for a civilization to expand and make its presence known. And yet, when we look up, the sky is silent. When we listen, we hear only the whisper of physics, the echoes of the Big Bang, the hiss of distant, unthinking stars. We see no grand engineering projects, no fleets of starships, no obvious, galaxy-spanning empire. This is the great contradiction. This is the paradox. It was most famously articulated by the physicist Enrico Fermi during a casual lunch conversation. He considered the numbers, the vast number of stars, the high probability of planets, the time available, and he asked a simple, devastating question that echoes to this day. Where is everybody? This is the Fermi paradox. The eerie, profound quiet in a universe that we expect should be bustling with life. It is perhaps the most humbling and thought-provoking mystery we have ever faced. It is not a problem to be solved, but a koan to be contemplated. Let us gently explore some of the possible resolutions to this silence. They are not answers but paths of thought. One path is that we are rare. Perhaps the emergence of life is easy, but the evolution of complex, intelligent life is extraordinarily difficult. This is the idea of the great filter. Imagine the development of life as a series of immense hurdles. The jump from non-life to the first simple cell. The jump from simple cells to complex cells. The jump from complex cells to multicellular organisms. The evolution of consciousness, of language, of technology. Perhaps one of these steps is so improbable, so monumentally unlikely, that almost no one ever makes it through. If the filter is behind us, for instance, the initial spark of life itself, then we may be one of the very few, or even the only civilization to have won this cosmic lottery. We are the survivors of an incredibly difficult journey. This thought is both lonely and precious. It would place upon us a profound responsibility to cherish and protect the consciousness that we represent. So far, the search has been met with a profound silence. But the scale of the challenge is immense. Where do you point the telescope? At which of the billions of stars? And at what frequency do you listen? The radio dial is vast. There is a concept, however, that gives searchers hope. It's called the watering hole. It's a quiet slice of the radio spectrum between the natural emission frequencies of hydrogen and the hydroxyl molecule. Hydrogen and hydroxyl, H and OH, together make water. The idea is that any water-based life form, like us, might see the poetry in this. They might choose this quiet, meaningful channel as the logical place to broadcast, a universal meeting point for civilizations to gather and drink from the well of knowledge. It is a beautiful, hopeful idea. And we have not only been listening, we have, on a few rare occasions, sent our own quiet messages out. In 1974, from the Arecibo radio telescope, we broadcast a simple pictorial message towards a star cluster called M13, some 25,000 light-years away. It was a simple postcard. It said, "This is who we are. This is what we are made of. This is where we live. Hello." The message is still traveling. It has not even completed 0.1% of its journey. It is a monumentally patient and hopeful act. A whisper sent into the vastness, not expecting a reply in our lifetimes, or in the lifetimes of 100 generations to come. But it is an expression of our own deep desire to be known. And so we listen. We listen for the chemical breath of a biosphere in the light of a distant star. We listen for the deliberate, intelligent pulse in the static of the cosmic radio. We are straining our ears, using the most advanced technology we have ever built, to hear a reply to a question we have only just learned how to ask. And what we have heard, so far, is the subject of our deepest meditation. The silence. Main content section 4. The eerie quiet, contemplating the Fermi paradox. Let us sit, for a moment, with this silence. We have journeyed through the cosmos and found it to be fertile. The ingredients for life are common. The number of potential homes of planets in habitable zones is staggering. Billions, perhaps trillions, in our galaxy alone. And our galaxy is but one of hundreds of billions. The universe has had over 13 billion years to work. Ample time for life to arise, for intelligence to evolve, and for a civilization to expand and make its presence known. And yet, when we look up, the sky is silent. When we listen, we hear only the whisper of physics, the echoes of the Big Bang, the hiss of distant, unthinking stars. We see no grand engineering projects, no fleets of starships, no obvious, galaxy-spanning empire. This is the great contradiction. This is the paradox. It was most famously articulated by the physicist Enrico Fermi during a casual lunch conversation. He considered the numbers, the vast number of stars, the high probability of planets, the time available, and he asked a simple, devastating question that echoes to this day. Where is everybody? This is the Fermi paradox. The eerie, profound quiet in a universe that we expect should be bustling with life. It is perhaps the most humbling and thought-provoking mystery we have ever faced. It is not a problem to be solved, but a koan to be contemplated. Let us gently explore some of the possible resolutions to this silence. They are not answers but paths of thought. One path is that we are rare. Perhaps the emergence of life is easy, but the evolution of complex, intelligent life is extraordinarily difficult. This is the idea of the great filter. Imagine the development of life as a series of immense hurdles. The jump from non-life to the first simple cell. The jump from simple cells to complex cells. The jump from complex cells to multicellular organisms. The evolution of consciousness, of language, of technology. Perhaps one of these steps is so improbable, so monumentally unlikely, that almost no one ever makes it through. If the filter is behind us, for instance, the initial spark of life itself, then we may be one of the very few, or even the only civilization to have won this cosmic lottery. We are the survivors of an incredibly difficult journey. This thought is both lonely and precious. It would place upon us a profound responsibility to cherish and protect the consciousness that we represent. N is the number we are looking for. The number of civilizations in our galaxy with which we might be able to communicate. It begins with our star. This is the average rate of star formation in our galaxy. How many new suns are born each year? This is a number we actually know reasonably well. Through our observations, we can see the stellar nurseries, the great clouds of gas and dust where stars are being born. The answer is somewhere between 1 and 3 new stars per year. A gentle, steady creation of new potential homes. Next is FP. This is the fraction of those stars that have planets. When Dr. Drake first wrote this was a complete unknown. It could have been that our solar system was a bizarre fluke. But now, thanks to missions like Kepler, we know this number is very high. It seems that most stars have planets. The current estimate is that FP is close to 1. Almost every new star comes with a family of worlds. Then comes NE. This is the average number of planets that can potentially support life per star that has planets. This is our Goldilocks zone question. How many worlds orbit in that temperate region where liquid water could exist on the surface? Our current data suggests this number is also encouraging. Perhaps 1 in 5 stars like our Sun has an Earth-sized planet in its habitable zone. The number of potential shores is vast. Now, the equation moves from astronomy into biology, and the numbers become far more uncertain. This is where we must be humble. FL is the fraction of those habitable planets that actually go on to develop life at all. The fraction where the chemical song actually begins. Is this number high or low? Is the jump from non-living chemistry to a simple cell an almost inevitable process, given the right conditions? Or is it a 1 in a trillion miracle? We only have one data point, Earth. Here, life seems to have started almost as soon as the planet was cool enough to allow it. This might suggest the number is high, but we simply do not know. If life does begin, we then have phi, the fraction of those life-bearing planets on which intelligent life evolves. Look at the history of Earth. Life existed for more than 3 billion years as single cells. Dinosaurs ruled for 150 million years, but never built a radio telescope. Intelligence of our kind, technological intelligence, is a very recent and perhaps very fragile development. Is it a common evolutionary outcome, or an incredible fluke? This is a deep, profound unknown. Then comes FC, the fraction of those intelligent civilizations that develop a technology that releases detectable signs of their existence into space, like radio transmissions. This is a question of sociology and technological pathways. Do all intelligent species become curious explorers? Or are some content to be poets and philosophers, never turning their gaze outward? Again, we are completely in the dark. Finally, we have the most poignant and sobering term, L. This is the length of time for which such a civilization releases detectable signals into space. How long do they last? Do they broadcast for a few centuries before they self-destruct, or run out of resources? Or do they achieve a stable, sustainable state and exist for millions of years? This single variable L is immensely powerful. Even if civilizations are common, if they each only last for a short time, the chances of any two of them existing at the same time and being close enough to communicate are vanishingly small. The universe is ancient. To find another civilization may require a synchronicity not just in space, but in time. And so, the Drake equation does not give us an answer. It gives us a beautiful framework. It shows us what we know and what we have yet to learn. It is a roadmap for our future explorations and a meditation on the chain of improbabilities that led to us. The science of distant atmospheres, reading the air of a ghostly world. Now, let us turn our attention back to that fragile light. The light that carries the chemical secrets of a world we will never touch. Let us go deeper into the magic of transmission spectroscopy. Imagine a distant star, a bright, steady candle in the dark, and orbiting it is a super-Earth or a mini-Neptune with a thick, puffy atmosphere. From our vantage point, light years away, this planet is invisible. But when it passes in front of its star, the star's light is filtered. The light we see is made of photons, tiny packets of energy. When a photon with the exact right amount of energy hits a molecule, the molecule absorbs it, getting a little kick. Every molecule, water, methane, carbon dioxide, oxygen, has a unique set of energies it likes to absorb. This is determined by the way its atoms are bonded together and how they can vibrate and rotate. So, when the full spectrum, rainbow light of the star streams through the planet's atmosphere, the water molecules snatch all the photons at their preferred energies. The methane molecules snatch theirs. The oxygen molecules snatch theirs. What emerges on the other side is starlight with very specific colors, or frequencies missing. These missing slivers of light are the absorption lines we saw earlier. The spectral barcode. This is the job of the James Webb Space Telescope. Its huge, gold-coated mirror is a giant light bucket, designed to collect as many of these precious, information-rich photons as possible. Its instruments are exquisitely sensitive spectrographs, able to spread that light into a high-resolution spectrum, revealing the barcode in incredible detail. The challenge is almost beyond comprehension. The amount of light that passes through the atmosphere, compared to the total light of the star, is minuscule. For an Earth-like planet around a Sun-like star, it's about 1 part in 100,000. That is like trying to detect a firefly flying in front of a searchlight from miles away. And then, from that firefly's faint glow, trying to determine the composition of the air around it. Takes time. For a single planet, the telescope must stare at it for hours, over multiple transits, patiently collecting photons one by one. The data is then painstakingly cleaned, removing the noise from the instrument and the star itself, until a clear signal emerges. A graph with dips and wiggles. Each dip is a clue. A dip at a specific infrared wavelength says water was here. Another says methane. Another, carbon dioxide. The depth of the dip tells us how abundant that gas is. This is how we are beginning to characterize the atmospheres of other worlds. So far, we have focused on large, gaseous planets, as they have thick atmospheres and block a lot of starlight, making them easier targets. We have found water vapor, methane, and even signs of clouds and hazes on these hot Jupiters. The ultimate goal, the holy grail of this research, is to do this for a small, rocky, temperate planet. A true Earth analog. The signal from such a planet's thin atmosphere will be incredibly faint, pushing our technology to its absolute limits. But if we can do it, if one day we point the Webb telescope at a world like TRAPPIST-1e and we collect the light and we see the barcode, and in that barcode we see the unmistakable combined signature of oxygen and methane, a sign of a profound chemical disequilibrium, in that moment the world will change. It would be the quietest discovery in history. A few photons collected in the cold of space. A wiggle on a graph on a computer screen. But it would be the first concrete evidence that the spark of life has ignited elsewhere. We would no longer be just looking up and wondering. We would be looking at a specific point of light in the sky and knowing that we share the universe. That is the power and the promise of this incredible science. It is the art of listening to the silence and learning to hear a symphony. Conclusion, the beauty of the question. And so, our journey through the quiet cosmos comes to a gentle close. We have drifted on a river of thought, from the stardust that forms our bodies to the great silence that fills our skies. We have seen that the universe, far from being empty, is a place of immense potential, seeded with the ingredients for life. We have visited the shores of other worlds in our imagination, from the rusty plains of Mars to the hidden oceans of Europa, and gazed upon the countless islands of exoplanets in the cosmic sea. We have learned how we listen, how we read the ancient light for the chemical breath of a biosphere, and how we strain our ears for the faint, intelligent pulse in the static. And we have sat, in quiet contemplation, with the profound mystery of the Fermi paradox, understanding that the silence itself is a story with many possible meanings. We have not found an answer to our central question. To the question, are we alone? The universe has not yet replied. And perhaps the true gift of this search is not the answer itself, but what the question does to us. It pulls our gaze upward, away from our small, terrestrial concerns, and connects us to the grand, sweeping scale of reality. It reminds us that we are part of a story that is billions of years old and billions of light years wide. It fosters in us a sense of humility, a recognition of how much we do not know, and how much there is still to discover. The search for extraterrestrial life is, in the end, a search for ourselves. It is a mirror held up to our own existence, forces us to ask, what is life? What is intelligence? What is our future? What is our place in this vast, beautiful, and silent cosmos? To know that the carbon in our hands was forged in the heart of a star, to know that the water in our bodies is common throughout the galaxy, to know that there are more planets than stars, this knowledge changes you. It infuses the world with a sense of wonder. It makes the night sky not a ceiling but a door. So, do not be disheartened by the silence. Let it be a space for awe. Let it be a motivation to be better custodians of the one precious example of life we know for certain, our own. Here, on this fragile, blue world, life has blossomed into a riot of complexity and beauty. Here, consciousness has awoken and is now able to look out and appreciate the universe that created it. This is a miracle worth cherishing, regardless of whether it is a unique one or one of many. The next time you are outside on a clear night, find a quiet place. Look up. See the countless invitations scattered across the velvet darkness. Feel the immensity, and instead of feeling small, feel connected. You are a part of that. You are a way for the cosmos to know itself. The journey continues. The listening continues. The wondering continues. Thank you for walking this quiet path with me. Keep looking up, and never lose your sense of wonder. Breathe in and out.